In your exam, you will get questions that involve graphs, and I've avoided using graphs. They're not the be all and end all of calculus, but you can't go far wrong if you think of things in terms of graphs. And in NCEA 2 and in IB, you will need to draw graphs and what different graphs look like when we integrate and when we differentiate. Okay, so here I've got GeoGebra. So I have the graph here is x squared plus, let's just bring this down a bit so you can actually see it. Whoops. That's better. So here we've got a graph of x squared minus 2x plus 3. So it's fairly familiar parabola. All right. And let's move it up a bit. What do we know about it? Well, we know from here it's sloping downwards and it has a turning point here and it's going up again. So it has a positive gradient. That's not really earth-shattering revelation there. Okay. Remember though that when we differentiate a function, we get the slope. So I've differentiated this function. Here you can test it out yourself that when we differentiate x squared minus 2x plus 3, we get 2x minus 2. So far, so good. Let's put it in. Okay, what do we notice about this? We notice here for values of x where it's sloping downwards, the gradient is negative. So the gradient is going to be below the x-axis. And from here onwards, our main graph, f of x, or y equals a function, is sloping upwards. So when we differentiate it, we're going to get a positive number, i.e. a number above the x-axis. So just remember that. So when we differentiate it, we're not really asking where it is. We're sort of saying what's the shape. And just to prove that we have this, at the turning point here, when the gradient is 0, it should be directly above or below a turning point. So I'm going to just put that line in there. So this is the graph x equals 1. There's a turning point where x equals 1 here, and it's directly above where it crosses the x-axis. Let's move it a little bit. And let's say instead of plus 2, it's plus 3, it's negative 2. So it moves down a bit. Notice that when we differentiate it, we get the same thing. Now, it's still negative there. So when we differentiate it, we get this nice blue looking line there. We have a turning point there where the gradient is 0. And now it's directly below where the gradient function crosses the x-axis and becomes positive. And from there on, it becomes more and more positive. So as this gradient gets more and more above the x-axis, this parabola here will get steeper and steeper and steeper. Okay, let's have a look at some actual examples from exams. So this is from the 2023 exam. So what have we got? Well, we've got the original function, the y equals function here, this kind of funky looking function here. And we're asked to draw what the gradient function for this graph here would look like on this set of axes here. Okay, let's have a look at it. So first thing we're going to do is we're going to look at the turning point. So there's a turning point there. So directly below it, so it's like 1, 2, so slightly less than negative 2. our gradient function is going to cross the x-axis directly below that. All right. From there, the slope is going to be is negative. So it's going to be kind of below the x-axis. And it's going to get less and less negative until we get here. And there's a turning point here. And remember, it's not where it is, it's the shape that we're interested in. So here it's about, what, positive 1.5-ish? So when we differentiate it, it's going to cross the x-axis there. And then there's another turning point here at around, what, 1, 2, 3 and a bit. So 1, 2, 3 and a bit, and it's going to cross it there. Okay. Below this point here, from there to infinity, there's a positive slope. Even though it goes below the x-axis, it's still sloping upwards very, very steeply. So therefore, it's going to kind of look like that. And it's just automatically put in a straight line for me, which I didn't really want. And then it's going from here to here, it's negatively sloped. So it's going to go below. What's going on there? So it's going to go below the x-axis when we graph it. And it's going to get fairly negatively sloped. So it's going to kind of look like that. And then it's going to kind of come up again. And then it's going to be positively sloped between here and here. Positively sloped. And from there on, it's going to be negatively sloped. So it's going to kind of look like an upside down N, or I don't know what that shape would be. But that's going to be the rough shape. So in order to get the marks, you need the rough shape. And it needs to cross the x-axis in the correct place. You need both of those to get the marks. Okay, let's have a look at one from 2024, last year's exam. So let's cut it off a little bit. So I'm just going to pause there for, oh no, there it is. It's just appeared like magic. So we have the original function here again. And here we have y equals f dash of x. So this, on this set of x's here, we need the gradient function. And in this one here, we have, I guess you'd call the original function. It's a terrible arrow. The original function. And this is the gradient function here. So let's have a look at what this original function is doing. First thing we want to do is find the turning points. And the turning point, there's going to be one there, and there's one there. So when we differentiate, it's going to cross the x-axis directly below that. So there's one there. So if we draw like a line down here, directly above that, and then there's going to be another one right there. So this is in a nice position here. About what? If these are 5, that'd be about 10. Okay, so we've got the turning points. So is it going to be above or below? Well, from here to negative infinity, it's negatively sloped. If we did a tangent, the tangent would be negatively sloped. So therefore, when we come to draw it, it's going to be below the x-axis because it's negatively sloped. Okay, so from here around, it's positively sloped from here to here. So therefore, it's going to be above the x-axis. And then it's going to get less and less steep. And then from here to infinity, we presume, it's going to be negatively sloped, and it's going to get more and more steeply negatively sloped. So it's going to kind of look like that. So it's going to be like an upside down parabola. And there is a kind of rule here. When we differentiate, we kind of lose a hump. We lose a turning point. So here there are 2 turning points, but when we differentiate it, we just get 1 turning point. And here we've got 3 turning points. We've got a turning point here, here, and here. So when we differentiate it, we're going to get 2 turning points here and here. So it becomes a more and more simple graph as we differentiate it. And that's pretty much all you need to know. There's not really that difficult. You just need to know we're interested when we differentiate it. We're not interested where it is. We're interested in the shape. We know that in the turning points, when we differentiate it, the gradient is 0, so therefore it must cross the x-axis, because the x-axis is where the slope equals 0 when we differentiate it. And when we differentiate it, we lose a hump, and conversely, when we integrate, we gain a hump, I guess. There is a thing that you'll do in university called Taylor series expansion, which exploits this. So it says that in, most functions, including the trigonometric functions, when we can convert it into a polynomial using calculus, and it's a really, really useful tool to have. You don't do it at school, but it is really, really important at university if you want to do anything involving mathematics at university, like engineering or physics or mathematics or economics or modeling, something like that. It's really useful. And that's about it, really.